In section 4 of chapter 3, we're continuing on our journey for the 95% confidence intervals, beginning, first of all, trying to estimate the 95% confidence interval on a single mean when the population standard deviation is known, then 95% confidence interval on the difference between two population means when sigma is known, then on a 95% confidence interval on a single mean where sigma is unknown and estimated by the sample standard deviation, and finally 95% confidence interval on the difference between two means when population standard deviation is unknown and is estimated by the sample standard deviation. So with that kind of an overview, right now, this is the topic of section 4. Let's do some theory. So in section 4 of chapter 3, we're interested in getting a 95% confidence interval on a single population mean when the population standard deviation is unknown and is estimated by the sample standard deviation. And so what I've got here are copies of two figures from your notes. Figure 4, which explains how to get a confidence interval on a single population mean when sigma is known, and then figure 6 in your notes shows how to get a confidence interval on the single population mean when sigma is unknown. So I'm going to review this and use that as a basis for making this comparison. So what did we see earlier when we were getting a 95% confidence interval on a single population mean when sigma was known? So we began with the underlying relationship. We're assuming that the underlying population is normally distributed with some mean mu and some standard deviation sigma. And from that, we get this. We can consider all the possible sample means that could be drawn from this population. And if we were to take all those means, all those possible sample means, and look at their probability density function, we would determine that it's normally distributed with the same mean as the underlying population, but because the big observations and the small observations tend to cancel out, we're left with a smaller standard deviation, which is sigma over root n. So this thing here is a probability density function. It's a particular kind of probability density function. It's a sampling distribution because it's the probability density function of a sample statistic. And finally, we can think about this idea that this represents the standard deviation of a normally distributed kind of population, so it has a special term which is standard error. So with all this in hand, what we did was we started off with y bar, we subtracted mu divided by sigma root n, and that gave us the normal distribution. Why is going to the normal distribution important? Because if we go to the normal distribution, then we can use our Z table. We looked at our Z table. What we were able to determine was the following. We determined our following. We went to the Z table, and we looked at 0.25 and the corresponding value of 0.975. So what's happening here is what we want to have here is 0.025 here. And what that means is that 0.95 or 95% of the population, or a probability of 0.95, lies within here. So what we're thinking about is the set of all possible observations of mean, sample means minus the population mean divided by the standard error, sigma root n. 95% of those we determined from our Z table would lie between minus 1.96 and positive 1.96. So we come back here, and that's what this is saying. If we consider the random variable, this is a random variable, the set of all possible values of y bar minus mu over sigma root n, that, and this p can be thought of as probability, the probability of these things lying between minus 1.96 and 1.96 is equal to 0.95. And then what we did was we did some dancing around the inequality sign, and we came up with this relationship, that the probability of y bar minus 1.96 times sigma over root n being less than mu being less than y bar plus 1.96 times sigma over root n was equal to 0.95. Then what we did was we said, okay, maybe we can generalize a bit. Maybe we're not always interested in a 95% confidence interval. Maybe we want some other confidence interval. Well, then we would just use the appropriate value of z to get that. And then what's happening here is just a reminder of what I said up here. This value of sigma root n that appears here, SE, where did that come from? It came from the fact that, remember, just as a review, if y is normally distributed with mean mu and standard deviation sigma, then the set of all possible sample means that I can represent as the random variable y bar is going to be normally distributed with mean mu and standard deviation sigma over root n. This is a sampling distribution because it's a set of all possible values of our sample statistic, and its standard deviation we can refer to as a standard error. So at this point, everything we've been dealing with is random variables. Now what we can do is we can draw our particular sample, calculate our particular value of y bar, plump it into that equation, and that's what gives us the 95% confidence interval that you would report in your thesis. So, having gone through all that, that's just a review. That's what happens when we're trying to estimate a 95% confidence interval on mu when sigma is known. So now let's go through this same process and think about what happens if sigma is unknown. So I'll do that on this side of the chart, and you can see how it corresponds on that side of the chart. So we're going to start off as before with the assumption that y is normally distributed with some mean mu and some standard deviation sigma, which means the set of all possible y bars is going to be normally distributed with some value. Mu is a mean that's going to be equal to the population mean, and a standard deviation sigma over root n. Here's where the change comes. Now we're going to assume that sigma is unknown. So now we can't use sigma. Now we're going to replace sigma with s. So if we replace sigma with s, what's that going to do? Well, that's going to introduce more variability into the relationship because we're confessing that we don't actually know what sigma is. We're going to estimate it with s. And so therefore what we have is no longer a normal distribution, but rather a t-distribution with some nu degrees of freedom. That's the symbol. It means nu or nu. Okay. Then what we're going to do is we're going to say, okay, we're just going to make this substitution here, s over root n. How about this 1.96, 1.96? If you notice over here, there's no longer a number given. So why is that? Why is there no number like 1.96 or minus 1.96 given here? The reason is that because we're dealing with a t-distribution, you don't know how to calculate the appropriate value of t until you know the number of degrees of freedom. So, unlike a normal distribution, unlike the standard normal distribution, the t-distribution has this other parameter, nu, which is the number of degrees of freedom. In our next step, it's really not that much different than what we did. What's going to happen between here is not that much different than what happened between here. It's essentially just dancing around the inequality sign. What we're going to have is y bar minus. Now, because we got minus 1.96 up here, because we're dealing with a t-table, we're not going to have a particular number. We're going to have something equivalent to this. And you can see, there it is right there. We have to have the appropriate t value. Now, we're going to have, instead of sigma divided by root n, we're going to have S divided by root n, because again, we don't know what sigma is. We're estimating it by S. Then what we do, we can draw a line here saying, okay, everything up until now is a random variable. So now how do we actually go about calculating our 95% confidence interval? Well, the important thing, and the reason that I actually went over this slide to compare this with that, is to show that operationally, it's not a heck of a lot different doing this and doing this. Because ultimately what you're going to do is get a sample mean, and in the case of a known standard deviation, which is very unlikely to happen, what you're going to use is Z alpha over 2 times the standard error. When you do it with a t-distribution, when sigma is unknown, it's essentially the same sort of process. You're going to have y bar. The only thing is that what you're going to do is substitute the t value, alpha over 2, instead of z value over alpha over 2, but you're still going to multiply it by the standard error. And remember what the standard error is. It's the standard deviation of the sampling distribution, the set of all possible values of lowercase y bar. Now we're going to do an example, and we're going to do an example with a very small sample. So we got these 5 numbers, 4, 4, 5, 6, 6. So the first thing we do is we calculate y bar, which is the sum of all the yi, divided by n, which turns out to be 5. Then what we have to do is calculate the estimate of the population variance by using the sample variance, and that's defined as the sum of all the yi minus y bar over n minus 1. And if you do the algebra, that turns out to be 1. So it's pretty easy to determine the sample standard deviation. That's just the square root of s squared, which the square root of 1 is going to be equal to 1. So now we know what s is equal to. We also need to think about what our standard error is equal to. The standard error is s divided by the square root of n, which is going to be 1 divided by the square root of 5. Then we need to know what our t value is. What is the appropriate value of t? To do that, we're going to go back to our t table. Here we are at our t table. And what we want to do is find a value that gives us 0.025 here. And because it's symmetrical, it'll give us 0.025 here. And also what we really want, as a consequence, is that there'll be 0.95 in this area. So that's what we want. We want 0.95 in this area. So the way a t-table works is a little bit different from the way a z-table works. First thing we need to do is figure out the number of degrees of freedom. We got 5 observations, so that means we're going to be in this row here. And the way this table is set up, what we focus on is this value of 0.25. That's what's shown in the table, is 0.25. So we come down here, 0.25 associated with 4 degrees of freedom is 2.77645. So let's go back to the whiteboard. Now that we're back to whiteboard, we can indicate that the t value was 2.77645. And then it's just a bunch of algebra. Our 95% confidence interval is y bar plus or minus the appropriate t value times the standard error. So y bar was equal to 5 plus or minus our t value 2.77645. We multiply that by the standard error, which is 1 divided by square root of n, which is 1 divided by the square root of 5. And if we do that all correctly, we should get a value between 3.8 and 6.2. So that's the appropriate 95% confidence interval on the sample mean when the variance of the underlying population is unknown and estimated by the sample variance. So just a couple of concluding comments. One of the things that it talks about in your notes is that, if you listen to the media, you'll oftentimes hear the statement being made that someone's gone out and done a poll, and it says that the results are that the margin of error was 5.4% 19 times out of 20. And that just doesn't seem to ring true to my ears. When I listen to that, I have a hard time understanding what's going on. I think what's going on is this. I think that folks in the media were told by statisticians that when you have an interval like this, there's a couple of things you can't say. You can't say that the probability of the mean lying between two numbers is such and such, because that's intuitively what people would like to think, but you just can't say that. Nor can you say that there's a 95% probability that the true mean lies between these two values. So what you're left with is what is reported. The margin of error was 5.4%, 19 times out of 20, which doesn't really sound right, but actually is probably a correct way of looking at things. And the second thing I want to consider is, why is it that so often polls are wrong? And to me, the big reason, other than the fact that, sometimes people lie, is how do you get a random sample? Because if you just go out and randomly sample a bunch of people and ask them who they're going to vote for, that isn't really a random sample of the true population. The true population, the mean of which you're trying to estimate, the true population is the number of people who actually show up on voting day and vote. And obtaining a random sample of those people isn't that easy to get. So, we'll stop there.